this video, I will be talking about two of the four reactions of alkynes that we're going to be learning about. These are halogenation and hydrohalogenation, both reactions that you're familiar with when it comes to alkenes. Turns out they're not that different when it comes to alkynes. I would ask that you read section 7.6, pages 263 to 265. It talks about these two specific reactions. Turns out halogens add to alkynes, so if you add one equivalent of X2, and notice that X could be bromine or chlorine, so this is Cl2 or Br2, you can add across the triple bond and it becomes a double bond. You're familiar with if you add to a double bond, it becomes a single bond, and you add two groups. Well, same thing is true here. If you add to a triple bond, it becomes a double bond, and you add two things. Notice I've drawn the two halogens across from each other, in other words, trans. Turns out that is correct. Turns out it's specifically anti. Notice that since we're adding the same thing to both carbons, two bromines or two chlorines, we don't have to worry about regio specificity. So you can stop at that point, and then you have an alkene with two halogens on it. It's a perfectly stable molecule. You can distill it, put it in a bottle, and so on. Or if you add another equivalent of X2 to that, or start with the alkyne and add excess X2, it goes straight to the single bond. So you've added two halogens across the triple bond to get this, then you've added two more halogens across the double bond to get to this. So then at that point you have a tetrahalide, four halogens, two adjacent carbons to each other. Here are some examples of that series of reactions. So here's an alkyne. We add one equivalent of bromine. We take the triple bond, turn it into a double bond. Two bromines are across from each other, or trans. This would be the E isomer because of the stereospecificity. Same idea here. Take an alkyne, add two chlorines to it, you end up they're trans to each other. This would be the E isomer as well. But if you add excess bromine across the triple bond, you go all the way from the triple to the single bond and you add four bromines to those four carbons. Same thing is true here. In this one I drew the reagent as excess. In this case I drew it as two equivalents. Either way is fine. This just means you're adding more than two equivalents. This means you're adding two equivalents, and you still get the same results. So to this triple bond, we're going to add two chlorines there and two chlorines there, and you get this molecule. Notice this looks a little confusing because it's all drawn in a straight line, unlike this one in which the bromines are drawn pointing up and down. In this one, notice that what we have is CH with two chlorines. That would be this CH with two chlorines, and then another carbon, that's this one, with two chlorines, and then the CH2, CH3. So this is just written in a straight line, whereas if those were hydrogens, it would be easy, but because of the chlorines, it looks a little bit more confusing. So this is really just a condensed form of this kind of structure. So what about mechanisms? Well, as we've seen, when you add halogen across a triple bond, you always get the trans dihalide. That's because it goes through essentially the same kind of mechanism. So notice that this is a three-membered ring with a halogen in it and a positive charge. This was a triple bond, now it's a double bond. It's a little hard to see in the structure, but that's a double bond in a three-membered ring with a positive charge. That's quite unstable, and so it immediately combines with the X minus that's left over, comes in from the back, attacks that anti-addition to give you a trans alkene. Really nothing new here, it's just working on a triple bond to make it a double bond instead of a double bond to make it a single bond. Here's the other reaction. Hydrogen halides add to alkynes. So if you take an alkyne, you can add one equivalent of HBr or HCl. The product is then an alkene with one halogen attached. So we've added one hydrogen to this carbon, so it becomes CH2, and one halogen to this carbon, so there is attached. But because this was a triple bond to begin with, this is now a double bond. Again, this reaction is really just like addition of HX to alkenes, but in that case you'd be starting with a double bond and going to a single bond. Here we're starting with a triple bond and going to a double bond. Now one thing to notice here is that the regio specificity is Markovnikov, which means the hydrogen ends up attaching to the carbon that already has the most hydrogens. With a triple bond, that means the carbon that has the hydrogen because it can only have one in the group. And so this really only is useful if this is a terminal alkyne, if one of the two carbons has a hydrogen. But if it is, then the new hydrogen will attach to that carbon that has the hydrogen, and it'll become CH2. The halogen will end up going onto the other carbon, as I've shown here. Now if we add excess HCl or HBr, it happens a second time. So this alkene adds another equivalent of hydrogen on that carbon, becomes CH3, and adds another halogen on that carbon, it becomes two halogens on the same carbon. By the way, that's called a gem dihalide. Earlier on we saw Bic dihalide is two halogens on adjacent carbons. Here a gem dihalide is two halogens on the same carbon. By the way, gem is short for geminal, which means twins, and it's because these two halogens are just like twins. They're exactly the same as each other on the same carbon. Notice the second equivalent, when we have the second equivalent of HX, it's also Markovnikov. So the first hydrogen added on here to become CH2, the second hydrogen also added on here to become CH3, the first halogen added on there to become CX, the second halogen also added on there to become two halogens. Now, what happens if you don't have a terminal alkyne? So what happens if your triple bond is in the middle of a chain somewhere? So you have two R groups. Let's say for the moment that they're the same as each other, so it's a symmetrical, non-terminal alkyne. Again, if we add HX to this molecule, we're going to add hydrogen to one, halogen to the other. Doesn't matter which one gets the hydrogen and which one gets the halogen. Not if the two R groups are the same as each other. So we get this kind of a product where the hydrogen's added to one and the halogen's added to the other. But notice that because the reaction is non-stereospecific, we get some where it goes trans and some where it goes cis. You get two products in that case. That's a little inconvenient because we don't want two products generally. We want one product. But the fact is, it really doesn't matter because typically we're going to add another equivalent anyway. And so we'll add another hydrogen on that carbon. And it really doesn't matter whether the first one goes up or down because once the second one goes on there, there's no stereochemistry there. The second halogen will go on the same carbon as the first halogen went on, and you'll end up with this molecule right here. So if the two R groups on the ends are the same as each other, it's pretty simple. You just add two hydrogens to one carbon, two halogens to the other carbon, and you make a single bond in between. But what if we add hydrogen halide to a non-symmetrical, non-terminal alkyne? In other words, this is a carbon group and this is a carbon group, but they're not the same as each other, so I put a prime on that. Well, now we have a mess because the hydrogen and halogen can add this way or this way. So this carbon can get the hydrogen and that one can get the halogen, or this one can get the hydrogen and this one can get the hydrogen. In other words, Markovnikov can't help us in this case. And that's the same thing with alkenes. We'll review that here in just a minute as well. So we're going to get two different cis molecules, and for that matter, two different trans molecules, because again, it's non-stereospecific. And if there are two R groups on the ends, then it's also non-regiospecific. So you get four possible isomers. Well, it's going to turn out that then when you add a second equivalent of HX, the new hydrogen is going to go on the same carbon that the old hydrogen went on, and the new halogen is going to go on the same carbon that the old halogen went on. So these two both become this, and these two both become this. So we do end up still with two products, one in which the two halogens went here and the two hydrogens went here, the other one of which where the two hydrogens went here and the two halogens went here. So you end up with two possible products. And they're going to be formed in roughly equal amounts, but not necessarily exactly equal. Unfortunately, that's just the way it is. So typically, addition of HX to an alkyne that's not terminal, and in which the two R groups are not the same as each other, not going to be particularly useful for synthesis because you're typically going to get two possible products. Now, just to remind you, as I said, the same idea of getting two possible products from a non-symmetrical internal alkyne is the same idea as what happens if you add HX to a non-symmetrical internal alkene. So if we added, this goes back to the alkene chapter, if we added HX to an alkene that had a double bond with two hydrogens, one on one carbon and one on the other, and two R groups that weren't the same as each other, then we would end up with some where the hydrogen goes here and the halogen goes here, and some where the hydrogen goes here and the halogen goes here. So we end up with two possible products. Again, not particularly useful. So here's some examples. So what would happen if you took propine, just plain old propine, and added one equivalent of HBr? This is the product you would get. You would add the hydrogen here, according to Markovnikov's rule, and the bromine here. That triple bond would become a double bond. That CH becomes a CH2, and the bromine adds on there. So bromine in the methyl group that was already on that carbon is still there. Now I've drawn this in kind of a more realistic 120-degree angle, sp2 hybridized as it is for an alkene. What happens if we started with 2-butyne? So again, this is one where it's not terminal, but the two groups on the ends are the same as each other. If you add one equivalent of HCl, you're going to have two possible products, the hydrogen and the chlorine trans to each other, the hydrogen and the chlorine cis to each other. But because the two methyl groups are the same as each other, there's just the two possible products. Well, what would happen if we had a non-symmetrical internal alkyne, in which one side had a methyl group and the other side had a cyclopentyl group? Well, then you're going to have some where the hydrogen adds on this end and the bromine on this end, some where the bromine adds on this end and the hydrogen on this end, trans, and some where the hydrogen adds on this end and the bromine on this end, cis, and some where the bromine adds on this end and the hydrogen on this end, cis. So again, 4 possible products there. That would be a mess if you wanted to make one of these 4 by doing it that way. Just would not work. Here's some more examples, but now we're adding excess. So what if you had 1 propine and you added excess HBr? Well, then it's a clean reaction. You put both hydrogens on this carbon, both bromines on that carbon, and you end up with 2,2-dibromopropane. What about this case where it's not a terminal alkyne, and so Markovnikov can't help us, but again, it doesn't matter because the 2 groups are the same, so whether we put the 2 chlorines here and the 2 hydrogens here, or vice versa, we're going to get the same product, which would be this one. It would be 2,2-dichlorobutane. But what about if we had an internal, non-symmetrical alkyne in which we're adding 2 hydrogens to 1 carbon and 2 bromines to the other? Well, again, 2 hydrogens here and 2 bromines here, or 2 hydrogens here and 2 bromines there. You'd end up with some of this product and some of this product, and there's just no way around that. You're just going to get those 2 products in, roughly 50-50. What about the mechanism of this reaction? Well, again, it's really not new. You already know what the mechanism for addition of HBr or HCl to an alkene is. Same thing here. So the first thing you do is use the HX to protonate the carbon that has the fewest carbon groups attached, in other words, the one that has the most hydrogens. So we're going to protonate that carbon, and it's going to give us a carbocation. So we get a carbocation at that carbon. So this pair of electrons comes in, is used to form the bond with the hydrogen. That leaves 2 bonds instead of 3, and that leaves this carbon missing an electron, so it ends up being positive. The halogen is then the conjugate base for the HX. Also turns out to be the counterion for that positive charge. So again, this is not new. This is just like what would the mechanism be if this were an alkene. Then, very quickly, that carbocation reacts with the X minus, forms a new bond in there, and you end up with the molecule in which you added a hydrogen and a halogen in the Markovnikov direction. So why does Markovnikov work here? Well, if you protonated that carbon instead, you'd end up with a positive charge there. That would be primary. In fact, if you protonate there, you end up with a secondary, and secondary is better than primary. So therefore, that's where it protonates, and that's where the halogen ends up. So here's some examples for you to do. So what if you were to start with 1 pentyne and had 1 equivalent of Br2? Go ahead and write that down. And here's the product. The bromine, 1 bromine adds here, 1 bromine adds here. You end up with a double bond and the 2 bromines across from each other, or trans to each other. What if we started with an alkyne that had a methyl on one end and an isopropyl on the other end? In other words, that would be 4-methyl-2-butyne. But this time we're adding 2 equivalents. Well, that's easy. You add 2 chlorines to this carbon and 2 chlorines to this carbon. What about this alkyne, which is terminal, and we're adding 1 equivalent of HBr to it? Well, that's easy. That carbon gets the hydrogen, that carbon gets the bromine, the triple bond becomes a double bond, and you end up with that molecule. No worries about cis or trans ever if it's a terminal alkyne. And what about this one where it's a non-terminal alkyne, but it's symmetrical, so the triple bond is in the middle? So then we're going to add 2 hydrogens to 1 carbon and 2 chlorines to the other, or vice versa. But because it's symmetrical, it doesn't matter which one gets the hydrogens and which one gets the chlorines. So I've drawn the product here where that one got the 2 hydrogens, so it just becomes a regular carbon in the stick figure, but you know there are 2 hydrogens there. And 2 chlorines to that carbon, so there's a 2 chlorines to that carbon. And that's the end of that lecture. Thank you for your attention.